Good afternoon, everyone. Hopefully, you're having a pretty nice time at the Cisco Live. My name is Devi Bellamkunda. I'm working as a technical marketing engineer focusing on enterprise business unit. So, before we get started, a little bit about me. Just like most of you guys, I like to explore food and culture of people living in this beautiful world because I'm quite fascinated by it because people across the globe live differently, have absolute different lifestyles, but their core values remains the same. And food is among them, and I love food. That's what I've been doing from the past 3 days. Uh, Before coming to technical marketing engineer, I worked for a service provider who provides cable, internet, and voice services to smaller towns and cities. And that's where I got to meet very nice people. And I also hold a CCIE in data center and service provider. And my current projects include SD-Access architecture's evolution and how SD-Access interacts with other domains and entities. And another project, the most important project that I'm working on that I took upon pandemic is brewing beer. I still remember whether it was my son or me who was excited looking at it, looking at the kit that I have. I brewed close to 10 to 15 batches, all the way from ales to lager, but porter is in my heart, so what you see is chocolate chili smoky porter. I was able to reproduce it, which means that I'm doing okay. Most of my friends are still alive, so I think I'm on the right track. So today we're going to see how, what use cases the SD-Access interacts with the firewall, the critical services, internet, and WAN. But before we do that, let's have a strong underlay and then move on to rest of the use cases. A quick level set here. We heard you. We heard all the customers and partners, not just the good, but all the troubles that you're running into when you're deploying our solution. So we came up with new capabilities to solve them. But I want to introduce you these new capabilities by telling you why we bought them in the first place. And the best way that I thought is by giving you a use case and story. And my wife tells me that I'm very good at stories when I come back home. So I think you're in the right hands. And again, I start with the assumption that you guys already have familiarity with the fabric and take on from there. And you would still have lots and lots of sessions over the span of this week for SD-Access. So feel free to attend it or watch the video even after the session. And the use cases that I try to bring upon here may not be your identical challenges or requirements that you go through, but they will definitely tinker your thoughts and give you ideas to explore with, to solve your network challenges. And there are quite a few places that you can explore your ideas with us here in the Cisco Live or with Cisco partners, CXs, and sales engineers. And these are the sessions across this week. And again, I wanted to tell you I want to tell you a lot of information and give you the information at the same time. So I've thought I've had lots of slides in the deck as for reference as well, which can help you for the later reference or when you look back at the same video as well. So I have a colleague of mine who's actively monitoring the session, so you could post your questions there, or you can even meet after the session as well. There is something new this time in the Cisco Live where you could meet the speakers for the respective session. So there is a dedicated session just for Q&A so that we can carry over the questions that we have. But this is sort of like a brand new session that you have to register for it. So please, this MTS 1059, if you can register for it, we can talk about it tomorrow as well if you have any questions. So I would like to give you a background of the use cases that I am trying to explain here. So we're going to look at an hypothetical customer, or sort of real customers, where I've consolidated the use cases into. So we are going to see what the challenges or the requirements that the customer is trying to solve. And as we move on to the presentation, we will see how are we solving those. The first one being the customer does need an overlay, but for every overlay, the underlay needs to be awesome. So you need a strong foundation for that overlay. So he wants to build the underlay in such a way that it caters to all the fabric needs. And he wants to do this simultaneously across the sites. Right? And another requirement that he has is enforcement on the firewall. So the policy enforcement that we speak about is always in the fabric, in the switches or the edge nodes, as we say. But there is firewall in every network, and there are various use cases where we would need to enforce the policies on the firewall. And he got into a situation where he bought a big convention center, such as this, and which would encourage all the vendors, it might be coffee shops or bakeries, and he would want the SD access network for this convention center to provide network connectivity to them. And he does not want to change any configuration on the fabric. And how does he do that? We'll see. And all the hosts in the fabric who are onboarded needs to have access to critical services such as internet and shared services, which might be DHCP, DNS. And folks that are familiar with fabric know that we need a sort of route leaking configuration which is needed outside of a fabric for a host to provide basic connectivity. But customer does not want to do that. Let's see how this is also solved. And the hosts which are onboarded should always have the internet up. It does not matter what happens to the upstream links or the borders, local to the site, remote site, their internet connectivity should always be up, is one of the major requirements for this campus or the customer as well. And at the same time, he does that, he needs to have a consistent policy propagation as well. And the last thing is he did invest in the SD-WAN for his remote branches, and the benefits of the SD access segmentation should preserve in the SD-WAN world as well. So these are all the requirements. Hopefully it makes sense why I needed to flash one at a time. So this is the customer's campus or location where he had a DWDM or high private links to connect all the buildings together. And if you see here, this is the convention center that he bought with a dome here. And Spotlight wants to sleep. And if we map these buildings to the sites that he's trying to migrate to the SD access. So he has a data center and a migration sites from all the way from 1 to 4, and you also have remote branches all the way over the mountains which are connected by SD-WAN, which needs to have this consistent policy as well. So these are the use cases and the respective sites that we're going to see as we move along. And I just did not show the wireless LAN controllers per site just to preserve space, but do think that they are also existing. So the first site that we migrate, right, we need to bring up the underlay, which caters to the fabric. And you already know about this with the DNA center LAN automation that we already have, through which you can automatically bring up the sites with the ISIS as your underlay. And what this does is not just automate your underlay with layer 3, but it also accommodates to the fabric needs, such as MTU, and also for any use cases where you needed multicast in the underlay, it caters to everything. And if you quickly remember the steps to bring up the LAN automation as to how simple it is, we would need a basic network settings to push to all these new devices, such as the DHCP, DNS, or any shared services settings. And once you define that, you would identify two devices which you call as a seed, and through which DNS Center can contact the devices and start this automation automatically, where it will initially discover the devices through a VLAN 1, which can go up to 2 hops down. And once the DNAC discovers the device and you stop the LAN automation, the ISIS point-to-point links are configured. This is something that you know. This is indeed one of the use cases of a customer, but if you remember, he does not want to do this one at a time. He wants to do this LAN automations simultaneously across the sites. And if we assume we take the LAN automation procedure and move this site to LAN automation, we consider these two devices as the seed, and then we discover newly discover the devices downstream. And if you see, these layer 2 links are automatically converted to layer 3, and then we can move this to a fabric where we can make these devices as border control plane nodes, edge nodes, and intermediate nodes. But how can we do this simultaneous LAN automation? And that is possible right now with a new DNS Center release, where LAN automation has a separate landing page right now, so it has its own home, and where you can start this LAN automation process, and you can visually see all the steps, which gives us more details, which, unlike before, we were trying to enhance this capability. And at a time, you can do 5 LAN automation processes. What you see here is 2 of them. And similarly, you can kickstart 5 automations, assuming 1 at a site. And this is available from DNS Center 235, and through which you can also add and delete links as we move on with the LAN automation process in a day end as well, which was not there before. And if you see, we were able to migrate one of the sites with Fabric underlay. And let's move on to our next requirement. And we'll also see the progress that we make as we move on these use cases. The first one being Fabric underlay. And the site of focus right now is headquarters, and the use case is firewall. But before we get to it, let's understand, or let's recap how we connect our SD access fabric to the outside world right now. So you have your underlay as ISIS, and you would bring your fabric devices, either border control plane node or edges, and you will use the eBGP IP transit handoff from your border nodes to the peer device, which we call it as a fusion. And you could either extend the segmentation as is with the virtual networks, and you can combine them either into a GRT or a global routing table, or preserve the segmentation. But you needed to do route leaking on this peer device to have access. And there are scenarios where the upper hop, the next hop to the border, can be a firewall as well. And the firewall also can do everything that a router can do, where you could do a route leaking between the virtual networks. You could either create policies on top of it. And this is what our customer is looking for. And if we come back to our story, the site of focus here is the headquarters. And the use cases that we're trying to solve is the enforcement on the firewall and the network access for vendors. So usually the firewalls are north of the fabric, pretty much similar to any routers that you have. So you would have a macro segmentation all the way from the border to the northbound of a firewall. So which means you have Lisp as your control plane in the fabric and VXLAN as the data plane in the fabric, which carries the SGT from the edge node to the border, and it is de-encapsulated, which means SGT preservation is gone. So from a data plane perspective, we can do BGP overflight from border to your firewall, but what about SGT? We can still carry SGT, but and this is specifically useful for scenarios where customers would want to statefully inspect the traffic within the fabric. And one way is to propagate these SGTs from the border node to the firewall with inline tagging. Ethernet inline tagging is one such propagation method where you can carry the SGT in the CMD header, basically in the layer 2 frame. But what this does is, the source SGT from the SD-access campus will terminate at the border, and the inline tagging will actually carry the SGT to the firewall. But for an enforcement, just like any access list, you would need both source and destination. You did send the source SGT. What about a destination? A destination can be anywhere in the data center or anywhere outside of a campus. So what we would need to do is, we can get the destination SGTs either via SXP or PXCRATE, which are the control plane propagation protocols which ICE supports. So when to use SXP and a PXCRATE? So SXP is the Secure Exchange Protocol, which ASAs or routers support, and PXGrid is a generic protocol, not just Cisco, other vendors do also support, which is little scalable from a configuration perspective. So having said that, you would get the destination SGT from the ICE. So let's put it into a use case. What are we trying to achieve? So this is specifically applicable in a data center scenario where the traditional data center does not understand the group information, but we would still want to enforce. So what we would do here is, we would send the SGT from the SD-access fabric, which is a contractor, all the way to the firewall via inline tagging, and we would have a servers outside of a fabric in the data center, such as a development server here, where we would assign an IP to SGT mapping in the ICE and send it to the firewall via SXP or PXGrid. And now if the firewall has both source and destination group information, we can enforce the policy on the firewall, either deny, permit, or allow as needed. But let me quickly show you what I mean by that. So in the demo that I'm going to show you two parts. The first part is, I would enforce the traffic on this firepower, which is integrated with the FMC, and I would send the tag from the SDA via inline tagging and enforce it here. And then I would remove the tagging and send both source and destination SGT via PXGrid from ICE and enforce. So I have a fabric built with Cat9K2 as my fabric edge and Cat9K3 as two edges, and then border and control plane nodes. So when you're trying to connect to a firewall, as I mentioned, this is just an IP transit, which is a basic BGP overflight configuration that you have. So I am basically extending this campus virtual network all the way to the firewall, and I'm doing a route leaking on the firewall and enforcing on the firewall, so that I can do inter-VN inspection also. So this is the IP transit, which I call it FTD transit. And if I quickly show you, I just wanted to show you that this is indeed a host which is connecting to it. So the host that we are trying to see here is 8.61 with a MAC address of 6993. And one important thing to note here is the Ethernet inline tagging is not automated from the DNS center. Either we can use DNS center templates to do it, or you can manually do it. So what I did here is basically I pinged the development server, which is outside of a fabric, which means that I have reachability to the server, and it is indeed going via this firewall. We can see that a source of 8.61 and a destination of 254.33 is indeed present here. And now what I would like to do is, I would like to create a policy on the firewall to deny the traffic. So what I am doing here is, basically I have SGT inline tagging enabled on the firewall, and I will enforce the policy on the firewall and see whether the traffic is indeed denied. This is what the customer wants to do, where he does not even want the traffic to be coming into the firewall or egressing out of the office network. And that is the beauty of the firewalls, where you can play around with the source being IP, destination being SGT, or both being either IP or SGT. So here what I wanted to show here is, I used a source SGT as employees and destination SGT as any. Because Ethernet inline tagging would only send you a source SGT. It will not send destination SGT. Once I deploy the policy that I've created, and I would, before I show you the process, whether it worked, I would like to show you that how I integrated ICE over PXGrid in the FMC. So the PXGrid connection would be to the FMC, but the Ethernet inline tagging would be to the firepower. So I have the FMC basically integrated with the ICE, and now let's quickly see what happens to the traffic and whether it is indeed getting denied in the firewall. So the traffic is indeed denied, and we can go back to the firewall and see that the traffic is indeed blocked. The traffic is blocked from 8.61 to 254.33. So now what I would like to show you is, I will remove the inline tagging and send both source and destination SGT from ICE. Because if you dynamically authenticate a host in the fabric, right, ICE does know about it. Or you could either just send the destination SGT off the development server and enforce both. But what I'm trying to tell you is, I'm trying to give you all the options of how simple it is to, and then enforce the policies on the firewall. So this is the SGT configuration that I have. And the SGT configuration is needed on a physical interfaces for a switches and sub-interfaces on a router. Because I have a switch, I have it on my physical interface, which I'm basically removing it. And now I will enable the policy again, but I will see the destination SGT of development server here already now. So I will use that destination SGT and create a policy from employees to destination SGT. So now the ping is dropped again, but this time we can actually see that on the firewall, the traffic is indeed denied from source IP to destination IP with the SGTs of both employees and production servers. So, but if you ask me, okay, I've understood I mean, I've seen the demo, but what is the recommended way? What are we actually doing? So I've watched these YouTube videos when I always wanted to buy a new phone. They always compare this Apple to Samsung, but the end they will say it's up to you. But I'm confused. But I'm not going to do that here. So if you want to enforce the policies using source SGT, use inline tagging. Because the tag is propagated in the inline header, it is very scalable. You could still use control plane propagation methods such as SXP or PXGrid to push to a firewall to enforce the policies, but it depends on what sort of a firewall you use and the memory limits of a firewall. So what is the recommended way? The recommended way or the scalable way is to send the source SGT from SD access via inline tagging and use the control plane propagation such as PXGrid to push the destination SGT and enforce there. So what if you're happy with it, but what if you run into a situation where you have SXP? You have a router that you need to enforce, or you have an ASA or a device where you need to enforce that do not support both. And we have an answer for that. As you know, SXP has been there for a while, but the SXP has evolved from version 1 to version 4, but it was never a VN aware. So what I mean by that is if you have 3 virtual networks and you would send the IP to SGT bindings from your ICE to a border node here, you would need 3 SXP tunnels, 3 manual configurations and 3 tunnels. And with new SXP version 5, you could send the VNs of your choice. You can send the VNs of your choice with a single SXP tunnel. So what you see here is you build a tunnel from this Cat9K reflector all the way to the border node. And I took an example of an SD access, but you could think of this like a regular branch as well. So you would build a connection from a Cat9K to this border and then send the VNs of choice. If you see here, even though I have 3 VRFs, I only send 2 VRFs, the VRF building management and building security. And if you see here, the export list is basically telling you what VRFs that you want to send, and the import group is basically tying the connection with the other border with 1113. And on the other side, if you see, there is a command called VRF. What it's basically doing is, it is basically saying, when you give me the IP to SGT binding, give me the VRF with it, and I can take it. So that's how we were able to successfully solve the partial use case of the headquarters. And now let's focus on the convention center that the customer is talking about, and which is migration site 3. So he purchased a convention center. He purchased a convention center where he would like to host events. And in the events, you would have all vendors coming from all over the place, where it might be a coffee shop or a bakery or anything. And they might have their presence in 2 different floors or 2 different places, but they need to still have connectivity to each other. And the important thing here is, for the sake of brevity, let's say this is the convention center's network. It might be huge as well. So you have bakeries in 2 different floors connected to a network. And if you think about it, in a fabric, the gateways or the Anycast gateways that we call were always on the fabric edges. But when you have these bakeries or any vendors, they will come with their own switches, and they will just need connectivity. All they would ask you to do is give me a port. I will connect my switch. I want network connectivity. And they would want the communication with the bakery in another floor, and they would want their credit card transactions to work, and they would want to preserve their own VLAN as well. And we can still do that with Fabric as well with something called layer 2 virtual network. If you remember, Fabric was always layer 3. If you created a layer 3 virtual network, there is an underlying Lisp layer 2 instance ID mapped to it. But here in this case, there is no IP here because the IP is actually outside the Fabric. The gateway is on the switch that is bought by the bakery. And there is another bakery who wants to talk to this gateway, and the Fabric is basically providing the connectivity. So what's happening here is this edge switch is responsible for sending the traffic from bakery floor 2 to bakery floor 1. So there is a layer 2 Lisp encapsulation created here, layer 2 instance ID, which encapsulates this traffic and then propagates it over. And this is also applicable in scenarios where you would want the gateways to be on the firewall. Right? There are scenarios where not inter VN, even within the VN, they would want the traffic to be inspected on the firewalls. And if the firewall is north of the Fabric, you could use a layer 2 border functionality to extend this layer 2 connectivity to the firewall. But let me quickly show you by a simple demo. So what I have here is a Fabric, and the bakery VLAN is 2002. So bakery came up with their own VLAN, and they have 2 switches in 2 floors, and they basically need connectivity, the same example that we took. Let's see how this is solved with Fabric. In the DNAC, so I already have a building 22, which is a Fabric that I have created. And you do not need to discover the devices. What I'm trying to show here is this is indeed connected to this Fabric edge. So 9200 L2VNI is one switch where the hosts are connected, the bakery floor 2, and you would have another switch which has the gateway, the 3560s. And in this example, I'm showing that both are connected to a single Fabric edge. It doesn't have to be. So if you see here, these are the layer 2 instance IDs that I've created. 8194 DNAC automatically gets it, but bakery underscore 22 is what I've created. There is no IP pool for it. I'm still preserving the VLAN of the bakery here. But let me quickly show you the workflow with a simple example. So you can create a layer 2 virtual network, which will guide you through the process, and it'll ask you to name a VLAN and give a VLAN ID. This VLAN ID might be of the bakery or any vendor per se. And the one thing to note here is for this to happen, the layer 2 flooding needs to be enabled, which LAN automation can take care of. And if you want to enable wireless functionality also, you can do that. So you can, once the workflow takes you through it, you can deploy the layer 2 virtual network. And let me quickly show you that they are indeed connected to the same Fabric edge. So now the VLAN, if you actually see, the VLAN 2002 bakery 22 have an instance ID of 8194. So we are actually tying the VLAN to a Lisp overlay instance ID. So Edge takes this packet and encapsulates it in the Lisp and then propagates it over VXLAN out. If you see, there is no gateway for it. There is no IP on the Fabric edge needed for this. And this is the configuration that actually gets pushed, where the VLAN is actually tied with the Lisp instance ID. And now let's quickly see the traffic. So this is the bakery where you have the gateway for this VLAN, and we will have another switch where we will try to ping the gateway, and then we will actually see that it is indeed propagated via this Fabric edge in the overlay. So here is the host. which is trying to ping this gateway 10.130.130.10. And you can actually see that the ping works. We can see that the MAC addresses of these are actually populated in the Lisp. So this is the MAC address of the actual host, E7, EF. So what I was trying to tell you is this is just one example. We can actually use this functionality as your network demands, where you needed to extend this layer 2 functionality over the fabric and preserving the VLAN at the same time. And that's how we are able to solve the second use case for the firewall, and this is our progress here. And now now we are coming into the more interesting aspect of it, which is the critical services access. And now the customer would want to have his host achieve the critical services access, such as internet and shared services, with no route leaking configuration. So if we quickly summarize the problem statement that we have, so the SD access fabric is there, and the hosts are inside the SD access fabric in the overlay, and the services are outside of the SD access fabric, DHCP, DNS, and for hosts to have access to it, we would need to do route leaking on a device which is north of the fabric. And the way we are solving is through something called SD access extranet. And we are solving natively within the fabric in Lisp. So who has the power in the fabric to do that is control plane node. As you know, control plane node in the fabric is the heart and soul of it, and which takes care of all the map requests and the replies that the fabric receives. So that has the capability to solve this use case. So what I mean by that is, the way we are solving this use case is by two terminologies called providers and subscribers. So what is a provider? A provider is something who is providing the services to you. So which can be shared services such as DHCP, DNS, or Active Directory, or an internet. So who is a subscriber? Everybody. Everybody in the fabric or a host which is part of a virtual network is a subscriber who wants access to these services that you provide. What ties up these two things? That is extranet policy. You create this policy in the DNA center and say who the provider is and who the subscriber is, and the automatic leaking is configured. It's all good. Let me wrap this around and put this into a topology. So if we look what we have seen and put it into a topology, you have two virtual networks, employee and a contractor. In our traditional fabric right now, without the extranet, we would need to send the segmentation, extend the segmentation to the peer device or a fusion, and do a route leaking here. But with extranet, what changes is you would only need to create or only need to hand off a provider virtual network. So what is a provider virtual network? A provider virtual network, as I said, it provides services, I know, but it can be anything. A provider virtual network can be any virtual network that you've created, or it can be your infra virtual network where you might get the default route from your service provider. So some key things to remember when creating a policy, this extranet policy, is you could build a relationship only between a provider and a subscriber. You cannot build a relationship between providers or between subscribers. So the key use case that we are solving here is providing the shared services access to hosts for inside a fabric to either shared services or internet, but not between subscribers. So let me quickly show you how exactly is this being achieved in the control plane that I talk about. So we will talk about two things. First, I will talk about the packet flow to shared services. How does this even work? So let's say I have an employee and a contractor trying to talk to a shared services which is north of a fabric. And for shared services, I would use anything such as internal border or an anywhere border to import the prefixes into my border. So which means my border node knows about shared services. And now I need to provide connectivity. So for that, I will create extranet policy as we just spoke about, where I will make a VN called shared services, and then I will make employee and a contractor as subscribers. And as you see here, you could have multiple subscribers to a policy, but you could only have multiple provider. You can only have single provider in a policy. So now when the edge node wants to talk to shared services, it is going to send the request to the edge node. The edge node is going to send a map request to the control plane node, which is a generic Lisp function, and it will ask for the shared services prefix. And here's the beauty. The control plane node will realize that there is an extranet policy present for this virtual network. And when it sees that, the first thing that is going to do is it is going to look up for that destination prefix in the source VRF who requested this information, which is employee. And it will not be there. So the next thing that it is going to do is it is going to look for the destination prefix in the provider VN, which it will be present. So the control plane would reply back to the edge node with the instance ID of the provider, the Lisp instance ID of the provider. So the traffic will be encapsulated in the VXLAN and sent from edge to the border node. That is why you only need to hand off the provider VN, because the traffic actually lands in the provider VN. But what about the return traffic? The return traffic, of course, the border node would de-encapsulate it and send the IP packet out. And in the return traffic, when the return traffic hits the border, there is this policy-based configuration pushed on the border to look at the subscriber VNs, and the subscriber VN of an employee would always have the prefix, and the prefix is then found out and then encapsulated in VXLAN and sent out. Let's look at the same process and visualize in an internet use case. In an internet use case, the difference here is when your northbound prefix is internet, we will not import anything. So all the internet routes are not known to the fabric, unlike shared services. So what happens here is we would create an extranet policy with a provider VN of internet and the subscriber VN of an employee and a contractor. And the extranet policy gets pushed to the control plane node. And when a host is trying to reach a prefix in the internet, the edge node is going to do the same thing. It is going to send a map request to the control plane node. But here's something different. The control plane node is going to look at the source virtual network of contractor, and the internet prefix of 8888 will not be available. It is going to look in the provider VN for the same prefix. Unlike shared services, here even the internet prefix is not available. But the border node registers the default route with the control plane node, and the control plane node will basically give notices which border nodes have the default routes present, and it will send the information back to the edge node with active borders with default route. So the edge node is going to send the traffic to the border nodes which has active default routes, which then border will de-encapsulate it and send it out to the outside world. And the same thing would happen for the return traffic. And the return traffic comes in, the border node detects the policy and looks at the subscriber VN, and the host would be present, and it would basically forward the policy back to the edge node. And you might have a question, what about the subscriber to subscriber? So I have created a policy of shared services with an employee and a contractor, but I do not want the subscriber to talk to another subscriber. What if you have a host and an employee wants to talk to a contractor, which it is not supposed to happen? It will not. So what happens is, when a host is trying to talk to another host, which is part of an extranet policy, they will ask the control plane node, hey, I need to get to this destination. What do I do? The control plane node will see that there is a policy associated with it, and it will reply back with, hey, you're not supposed to talk to it, with a map cache action, map reply with an action of drop. So let me quickly show you what we just spoke about. In this topology, what I'm going to do is I'm going to create this extranet policy called first policy with a services VN as my provider and a subscriber VN as a campus. And see how my host gets an IP automatically without route leaking. I have a fabric up here already. So first, what I would like to show you is the virtual network itself. Here, I have virtual networks of both campus and we can see all the virtual networks here. Virtual networks of the policies, campus, and then the services. First, I'm going to name the policy. And then it is basically asking me, what is your provider virtual network? So the provider virtual network is where your services are. I have created a VN called services. You could actually use infra virtual VN also as your provider virtual network. And here it is going to ask for who are your subscribers. You can add how many ever subscribers that you want as part of a single policy. That is all. So user will have an option to whether to push the policy right now or even later. So that is, you can even push this extranet policy to how many ever sites that you want. That is as simple as it. So let me show you what it's actually pushed. If you look at the border node first, the BGP relationship with the next hop is up. And then if you look at the control plane node, is where the configuration is actually pushed. The campus being the 4099, which is the subscriber, and services is the 4101, the provider. And you can see the extranet policy is indeed configured on the fabric control plane node, and we can also see the entire configuration for it. But one thing to remember here is, if you have an SD access transit scenario where 10 sites are connected, how do you apply the policy? While you are applying the policy, if you click one site, the DNS center will auto-detect it and push it to all of the sites. And this is the actual policy that I was talking about. So the actual leaking is on the control plane node. If you see, my host actually got an IP of 8.2 already from the DHCP server, and you can see the MAC address of 08C4, and it is actually indeed connecting to the fabric edge. The VLAN 81, the gateway is here, and you see here there is no the Lisp instance ID, there is no subnet associated with the provider. Because the VN information is actually in the subscriber, the provider will have no IP address. Unlike before extranet, where every virtual network needed an IP pool. That is how I have IP address for the host. And the summary or the takeaway that I want you to go from this section is the route leaking is automated from the DNS center via extranet policies, but this is meant for a shared services or a critical services access, but not for subscriber to subscriber. If you have use cases where you would want to enforce policies on the firewall, or firewall needed to take the traffic or inspect the traffic, we would need to go with general traditional route leaking. As you've seen, the reason for this is the traffic is actually landing in the provider. We are natively doing the leaking and sending the traffic in the provider. If you would want to inspect the traffic in the VNs, that is not possible. Yes. Good question. The question is it possible to have a multicast subscriber in the services in the provider? We are actually working on it. Currently, the multicast services cannot be propagated from a subscriber to a provider. But if you have multicast services within a VN, if an RP and a receiver source or within a VN, it works, but it cannot traverse this extranet policy, but it is actually in the works. It will be possible for sure. And I have listed in the references in the deck as well. So now let's talk about the seamless internet use case. Here is our progress chart, and what the customer wants from the seamless internet is, he would like a policy that you have created in the SD access to be propagated across all the sites and have internet up all the time. And this is achieved by two things. The first thing, which you already know, is the SD access transit, which preserves the segmentation across the sites. And the second is the Lisp publisher and the subscriber. Let's look into that. The first thing is the SD access transit. Before we get to that, what exactly is a transit? So if you are trying to get to a destination, so if you're flying from destination A to destination B, and there is a transit in the middle, that is indeed what a transit here is. If your destination is either a data center or an internet, you would use something called an IP transit. If you want to provide connectivity between the sites, you would use something called an SD access transit. That is in an essence. But if you look at the IP transit that we have right now, this is specifically used for services where we do not control, like an LTE or a backhaul network, where we do not have control, where we can accommodate the VXLAN headers that we have. So which means that the SGT propagation over the WAN gets tricky, and we might have to rely on other manual resources or configurations such as SXP that we have seen before. This is not what customer wanted. And for the customer's use case to work, the SGT needs to be propagated from all sites, from site 10 to 20. And this is possible with SD access transit, where the control plane protocol is Lisp all the way, and the data plane is also all the way, which is same with SGT. So the SGTs are indeed carried in the VXLAN end to end. And even our controller is the same. So you could automate all this via DNS center and achieve the segmentation at the same time. And what about Lisp PubSub? What exactly is it? So Lisp publisher and a subscriber is a new control plane protocol control plane architecture, let me say this, which we have come up with recently. And what is the difference? Like, why did you even come up with something like this, and what is the difference, you may ask? So we have Lisp BGP, which we released in 2017, and the PubSub came in 2021. So what we were basically doing is we've heard from all of you guys while you were deploying and the issues that you're running into, and we wanted to solve the use cases and also bring in latest functionalities on top of it. So what we did was we built a framework called Lisp Publisher and a Subscriber, which is a faster way to propagate the exchange or propagate the messages in the fabric. So what are the messages in the fabric? So the map requests that control plane receives from edge nodes, border nodes, transit control plane nodes, all these are faster. And when we built this new framework, it helped us solve multiple use cases, such as dynamic default border, Lisp backup internet, and extranet. Let me get to all of these. So, as I said, before PubSub, we went with a hybrid approach, meaning Lisp is an overlay protocol which thinks about, hey, host is my end IP address, and I have a RLock or a routing locator, which is a loopback. So it built a table with EID to RLock mapping. And the external connectivity was always BGP. How does Lisp talk to BGP? So what we did was we went with something called BGP VPN v4. So we used to propagate the endpoint information from the border to the transit control plane node, or from the control plane node to the borders, and then the border is going to put that into the map cache and propagate it over. So what basically happens here is the border node, not a Lisp known protocol, I could only send IP address. The RLock information is not known. But if the border does not know where to send the traffic, it will drop it. So we used to create an incomplete map cache entry. Map cache is nothing but a Lisp forwarding entry on the border to populate the map cache. So meaning when the traffic receives the border will have an extra map reply to control plane node to populate it. So let me put that all into this example. So let's say you have a data center who is and who we have internal borders, control plane node in site 1, and we also have external borders in site 2. As you know, transit control plane nodes are the heart and soul of the SD access transit. So now first what we do is we have an eBGP relationship between a data center and internal borders. So the data center, the prefixes are imported into the internal border, and the internal border will have an iBGP relationship through which it propagates the prefixes to the control plane node, and it will register that prefixes to the CP. Because CP should know about everybody. Once the CP knows about the presence of everybody, it can steer the traffic, or it can do a map replies accordingly. Now in the control plane node, currently it acts as a BGP route reflector. So it reflects the information, and at the same time, it will send the information to the external border in a way where external border will put the prefix in the map cache. So the external border is doing that because when you receive a traffic from other sites or from the outside world, it can realize that I need to ask the control plane for it. So external border is going to put that into the map cache, and it will register those prefixes with the transit control plane node. Because when you have an SD access transit, the prefixes in site 10 also needs to talk to this site. And the same thing would happen on the other side. So if you ask me for a summary of this slide, it is working with Lisp BGP, but we went with a hybrid approach where you needed more control plane messaging within the fabric. So we made this fast with PubSub. So what did we do? So what happens here is we build a publisher and a subscriber relationship. So the first thing is you have an eBGP from data center to the internal border. Then you have a publisher and a subscriber relationship for everybody. So all the registrations are done on the PubSub, and once you receive the registrations, they are either put them into the database or map cache automatically. So the reason that it was so simple is we are relying on a single protocol which knows about both prefixes putting in the map caches or the databases. And another advantage with this, the reason this helped us with new use cases is this was not just helping in the messaging services, it was also sending the priorities of Lisp and other IDs, which helped us achieve other use cases. And that is why extranet is also possible only with PubSub. So now, how does it even work here, right? I said PubSub is good, but who is actually publishing, who is actually subscribing? So in the PubSub, you have publishers and subscribers. And as you might have correctly guessed, control plane nodes and the transit control plane nodes, the masters of the fabric, are the publishers. As the name suggests, publishers means they know about the prefixes of everybody. If it's a local site, local CP would know. If it's a remote site, transit CP would know. So who needs this information? Border nodes. Border nodes being the egress and the ingress part of a fabric, they would need to know this information when to send the traffic out, and if the ingress traffic is receiving, where should I send it? The difference between the BGP and the PubSub here is, once the traffic comes to the border knows about everybody. The map cache is automatically populated. So the traffic between east-west is super fast. And as I said, the publishers are the control plane nodes, and the external border nodes are going to subscribe to only control plane nodes and transit control plane nodes, because they connect to the outside world and SD access transit. And the internal border nodes only subscribe to the local control plane nodes, as the example that we have seen before. And if you have publisher and a subscriber in the same box, you would have a relationship on the same box. And if you ask, like, okay, you already have a Lisp session, what is this? So the publisher and the subscriber sits on top of the Lisp session. And if you see the configurations, if you compare the configurations, because we are not relying on BGP, all the configurations are sort of simplified. And now that we have seen the framework, what is this advantage? Dynamic default border is a marketing name that we came up with so that no one can identify what this is. So this basically means that this is a border convergence feature. So what it is let's just understand what the problem that we're trying to solve here. In the Lisp BGP world right now, what happens is when a border node reloads, when the border node reloads, we lose the default route. And when the border node comes up, you have IGP as ISIS and you have EGP as EBGP. And IGP converges faster than EGP. So once the ISIS comes up, edge nodes, the data center prefixes, and the SD access transit prefixes start sending traffic to external border node, and you have a black hole. And the other problem is if you have an upstream link down. When the upstream link is down, EBGP is down, but your loopback is still up. Everybody in the fabric is sending the information to the border node. And to avoid this, we were using IBGP or EM scripts to get around this. And with PubSub, you don't need any of this. You don't need any of manual configuration. How are we actually solving this? But before I explain the solution, let me first tell you why or how is it working with BGP right now, so that we can actually compare where is it getting better. With BGP, if a host is trying to access a prefix, an internet prefix, the edge node will get the information, it will send the map reply, or basically ask the control plane node, hey, I want to talk to a prefix in the internet. And control plane node will not have this. He's going to say, no, I don't know. It is going to reply with something called a negative map reply, which basically means that I don't know what to do. So in these scenarios right now, we have something similar to static route in Lisp, which is use PETR, use proxy ETR, and we give or DNSE configures the border configuration. So it behaves exactly like a static route. It does not know what happens upstream. It is just going to push the traffic to the border node or the use PETR, the loopback address. So once the NMR is received to the edge node is going to encapsulate it in the VXLAN and send it out. That is why we were running into all these problems. And we had to rely on IBGP or templates. How is PubSub solving this? With PubSub, what happens is the host would request for the internet prefix and it would ask the control plane node. Here's the beauty. Every border node who has the default route will register with the control plane node and the transit control plane node over PubSub. So when I say register, we are basically watching the rib. So border nodes are going to say, hey, I have default route to CP. And to transit CPs, hey, I have default route. When the default routes are gone, they are going to say, hey, I do not have a default route. And they are going to send the deregistration with a priority of 255 so that control plane node knows that, hey, this guy does not have a default route. So the control plane node here will send the reply called unknown map reply. In the unknown map reply, it is going to send the loopback informations of all the borders with active default route. So the edge nodes would automatically put this in the map cache and send it out. And this logic is so beautiful, it not just helps in single-site convergence, in a multi-site convergence as well. So what I mean by that? So, and as I said, it would register with the local CPs and TCPs, and the deregistrations happens with a priority of 255, so that when the edge receives the border node's loopback, it would use the borders with lower loopback. And that is the beauty of the PubSub's framework. We were not able to just send the map replies, we were able to send priorities. If we quickly put that all together and compare with a simple topology, with a BGP, if we are trying to talk to the internet, it automatically load balances between the borders. And if a router goes down, as we discussed, the same problem arises. We were either leveraging IBGP or templates, and the traffic traverses via other border. And if the default route goes down, same thing happens. But with PubSub, what happens is the external borders are going to register the presence of the default route, and traffic automatically traverses via the external borders. But when the default route goes down, it is dynamically steered because all this process happens very fast. And the same thing applies even when the border node is down as well. And if you think about the same logic in an SD access transit scenario, because the border is not just registering with the local CP, it is also registering with the transit CP. As you know, the transit CP sits in the middle and he knows about every site. He knows about aggregates of every site. So when some other site is trying to talk to this site, he will know that, hey, if you want to talk to this prefix, it is the RLOC of this border. But the good thing about, or the advantage with this feature is, border nodes are also registering the presence of a default route. So he knows that which site borders have active default route. So basically extend the logic of dynamic default border across SD-access transit. Now if you put that into a bigger use case is what the customer wants. The internet should always be up. So the traffic automatically traverses via these two external borders. When the upstream link goes down, the traffic is automatically traversed via another external border because the control plane node knows about it. The actual thing what happens under the hood is if the edge node is actively sending traffic to the external border and the upstream link goes down, the external border, when it deregisters the default route with the CP, it also sends a message to the edge node saying, hey, something is wrong with me or something changed in my table. Please re-update your table. That message is called in Lisp solicit map reply. When edge receives that information, edge is asking the CP again for the updated map cache, which it received. So here, it is good. One upstream link for one border goes down, it traversed by other border. What if the other border link is also down? That is what our customer wanted. The host internet should always be up. The internet will traverse via other side border. Reason being, the transit CP would know about the presence of who has the active default route, and they will steer the traffic or they will reply to the external borders with the RLOC information of other sites. But for this to happen, I assume that you're familiar with SD-access transit, where you need to say that the internet for this site is indeed shared. When you click this button only when the external borders will register the default route with CP. There are use cases where customers does not want to share the internet access to other sites because of the lower bandwidth links. In those cases, you do not have to. In summary, the local internet is always preferred over the backup internet. So the CP would always know that it has a local external border link up, and it would only prefer the local, and only if both are down, only then the external borders in other sites are used. There might be sites like remote access site where there are branches and they do not have local internet at all. But how do we have access to internet for in-hosts in these scenarios? Same beautiful logic. Transit CP knows about who has the active default route. These two guys. So when the edge node is trying to, in the remote site is trying to get to the internet, it will automatically load balance the traffic between the external borders in site 4 and site N. Let's make it more complicated. What if the customer wants to send the traffic to only site 4? The remote SD access site wants to send the traffic to only site 4, which is an absolute valid use case because he might have spent money in purchasing an expensive upstream link in site 4. He would want the traffic to go via site N only when the internet is down in site 4. And that is also possible with Lisp priorities. So in the border node, you have an option to configure the Lisp priority. The priority values can be from 1 to 9. If you do not configure anything, the default is 10. That is why the traffic is load balanced. And if you tweak the traffic, if you tweak the priorities, like in this case, which is 6 in site 4 and 9 in site N, which means that remote SD access site would always use site 4. But you get the logic. That's what I wanted to share. Sometimes you might want to play around with the priorities even within a site, but that is possible. And the way you can modify the priorities is under the border node. But this is possible in both Lisp, BGP, and PubSub as well. And there are other deep dives on what happens under the hood. There are quite a few things that happens under the hood. If you want to learn, you can go to the Lisp sessions and the other SD Access Transit best practices also. But we spoke about quite long for this, but what are the actual takeaways for this use case or this section here? If you want to traverse, or if you want to traverse the SGT from one site to another site or one site to every site, SD Access Transit is the way to go. And the PubSub is the new control plane architecture, which not just enhances the control plane framework by reducing the number of map requests, but it also paved way for more use cases for SD Access Fabric, such as all these. And everything else that we spoke about until now is automated by DNA Center. Now the network looks perfect. So we just have two more branches to deal with, which is the WAN. And before we get to that, let's quickly map our control planes to data planes, the differences between our SD Access domain and the SD-WAN. So you have Lisp in the SD Access, and then OMP in the SD-WAN, and then you have VXLAN, which is an IPsec. So how, and even the management plane is different. How do we even propagate these SGTs together? If you remember, we had two small branches, and we also had a migration site 3, which we needed to get the segmentation benefits for SD Access to SD-WAN environment as well. So there are some sites where the customer would like to automatically get the port usage. In those branch use cases, you could use Fabric in a boxes and enable embedded wireless functionality as well. And you can still propagate the SGTs even from those branches as well. And if you remember, this is our migration site 3, where we have already migrated to SDA, and we'll move all the upstream routers to our C edges. And once the upstream routers are moved to the SD-WAN functionality devices, then what happens is we need to get the policy constructs. So what are the policy constructs? Policy constructs are both VN and SGT. So for that to happen, the VN in the SD Access need to map with virtual or VRF or VPN in the SD-WAN world. So we need to, the only configuration or the manual configuration that needed for this to work is the IP transit config from the border nodes to the C edges, which is automated, but the C edges does not understand or does not have OMP configuration. So we needed to enable BGP on it and configure the inline tagging as we spoke. So this is the piece where we need to enable the inline tagging and BGP configuration. So what basically happens here is the tag which de-encapsulate in the VXLAN is put it in the .1 queue and sent to the WAN edge. WAN edge takes the tag and de-encapsulates it from the .1 queue, puts it in IPsec, and carries it over. And that is how we are able to successfully solve all the challenges and requirements of this customer, and you have a happy customer who has a network for the future. And please remember to register for the session. If you have any Q&A, we can carry over to the other session as well. And we have written a book in the few months ago, where rather than focusing on the SD Access functionalities, we started to focus on the verticals. So this book actually talks about verticals such as healthcare, enterprise, and the common use cases that they've run into and how you can solve those use cases with SD Access. The QR code actually helps you download the PDF version of it as well. And please let us know the feedback. And this is the holy grail, or the common source of truth for us as to what platform supports, our platform support is in the SD Access world, and what versions and what platform support, when did it come out. This is the source of truth. And if you have any questions regarding the platform support, or if it is there, if it is not there, there is a help button where you can directly contact the engineering, and they will help you with a response. And if you are planning with an SDA, you needed to know the scale of not just the DNA center, but also the routers and the switches. How many APs or how many hosts does it support? And this scale document would help you. We keep updating the scale document for every release. And that is all I had. Thank you so much for patiently listening to the session. And I'm still here if you have any questions. I tried to give you the intention of why we even came up with it. And to be very honest, the feedback from you is what helped you give the best of the solution. And it is still needed for us to enhance it more. Thank you.